we will now prove an important theorem. Let X S mu be a measure space let 1 less than or equal to P less than or equal to infinity, then LP mu is a Banach space. So LP is a space of equivalence classes with respect to relation of equality almost everywhere with the P integrability norm, and or if it's essentially bounded, then it's norm infinity, and so each of these spaces is complete. Okay, so proof. So first case, we'll take 1 less than or equal to P strictly less than infinity, because these involves integrals, so the arguments are slightly different. So let Fn be Cauchy in LP mu. So we have to show that this converges to some function in LP. Okay, so enough to show there exists a convergent subsequence, because if you have a Cauchy sequence and you have a convergent subsequence, then the entire Cauchy sequence will converge to the same limit. So it is enough to show there exists a convergent subsequence. Now, because you have a Cauchy sequence, you can always find a subsequence such that consecutive terms are as close to each other as you prescribe. This we have done several times before. So choose subsequence Fnk such that norm Fnk minus Fn k plus 1 in LP is less than or equal to 1 by 2 power k. So you can always do this. So, and we now define Gn of x equals sigma k equals 1 to n mod Fn k plus 1 x minus Fn kx. Okay. And then you define G of x equals sigma k equals 1 to infinity mod Fn k plus 1 x minus Fn k of x. Okay. So then of course you have that Gn increases to G. So it's a monotonically increasing sequence for each x, because you are taking 1 to n and then you are adding positive terms more and more. So this is a monotonically increasing sequence, and you have that it increases to G of x. Okay. And also by the triangle inequality, norm Gn in LP is less than or equal to norm of Fnk plus 1 minus Fk in LP, that is sigma 1 to n 1 by 2 power k, that is a geometric series, and I can estimate it higher by 1 to infinity, so that is less than or equal to 1. So 0 is less than or equal to Gn and it increases to G, and norm Gnp is less than or equal to 1. So by the monotone convergence theorem, you have norm Gp is also less than or equal to 1, because the integral of mod Gn power p will converge to mod G power p. Okay, that is the monotone convergence theorem, and therefore mod Gp is also less than 1. So in particular, we have Gx is finite almost everywhere, so except on a set of measures 0, because its p integral is less than or equal to 1, so it cannot be infinity on a set of positive measures, so it has to be finite everywhere. Okay, and further, if k greater than equal to L greater than equal to 2, then you have mod fn k minus fn L of x, okay, is less than or equal to, by the usual, fn k x minus fn k minus 1 x plus mod fn k minus 1 x minus fn k minus 2 x, and so on, and you have to go on, plus mod fn L plus 1 x minus fn L of x. Okay, now this is, what is this? This is nothing but gn k plus 1, gn k minus gn L minus 1. So this is equal to gn k, yeah, because gn k x minus gn L of x, not nk, gk of x minus gl of x, L minus 1 of x, and therefore that is less than or equal to gx minus gl minus 1 of x. Okay, but you know that gn converges to g pointwise almost everywhere. Therefore, for almost every x, we have fnk minus fnl is less than or equal to gx minus gl L minus 1x, which goes to 0 as L tends to infinity, and therefore fnkx is Cauchy. And therefore you let f, so fnkx, let us say, so limit, so define equals fx whenever it exists, and 0 elsewhere, and this is on a set of measure 0, because almost everywhere it converges, and therefore you have this. So we now have a candidate, and we have to check if this candidate is in LP and if you can converge in LP. So if you, so gn minus gl minus 1 is of course less than or equal to gx also. So that is, you already have. So now if you take L tending to infinity in this thing, so you get mod fnkx minus fx is less than or equal to mod g of x, almost everywhere. Okay, so because except on the set of measure 0, there everything is 0 and we don't have to worry. So G is in LP because norm GP is less than or equal to 1. FNK is in LP because it's a finite sum of, it's anyway in LP, that's given to you. So this implies that F belongs to LP. Okay, and then what? You have mod FNKX minus Fx power P goes to 0 almost everywhere, of course, and bounded by Fnkx minus Fx power P is less than or equal to G power P, and this is integrable because integral G power P is less than or equal to 1, and consequently by the dominated convergence theorem we have that integral mod Fnk x minus Fx power P over x d mu goes to 0, and that is Fnk converges to F in LP mu. So we have subsequence which converges in LP, therefore in the original sequence being Cauchy, so Fn Cauchy, since Fn Cauchy we have Fn itself converges to F in LP mu. Therefore, LP mu is complete. Okay, so now that completes the case where P is strictly less than infinity. So case 2, P equals infinity. So you have Fn is Cauchy in L infinity mu. So for every k natural number or positive integer, there exists nk such that norm fnk fm minus fn is less than 1 by k for all mn infinity, for all mn greater or equal to nk. Okay. Now what does this mean? So that is, there exists ek contained in x, measure of ek is 0, and for every x in ek complement, this is equal to x minus ek, okay, we have mod fnx minus fmx is less than 1 by k. That is what we mean by saying that, because this is essential supremum and therefore it is valid except on the set of measure 0, and this is true for all mn greater or equal to nk. Okay. So now you take E equal to union ek, k equals 1 to infinity, okay, and then mu of E is a countable union of sets of measure 0, and therefore mu of E is also 0. And what is E complement? So E complement is intersection k equals 1 to infinity ek complement. Okay, so if you take every x is in E complement is in every ek complement. So if x, for all x in E complement, you have, which is the complement of a set of measure 0, you have for every k and for all n greater or equal to nk, you have we have mod fnx minus fmx is less than 1 by k, and therefore fnx is Cauchy, uniformly Cauchy in fact, in E complement. Okay, so you take fx equal to limit fnx on E, and then you can take in fact 0 on E complement and 0 on E, for instance, if you like. Okay, so then you have, if you allow m to tend to infinity, you have mod fnx minus fx is less than 1 by k for all less than or equal to 1 by k for all x in E complement and for all n greater or equal to nk. That is, f belongs to L infinity and fn converges to f in L infinity. Okay, so that completes the proof of this theorem, that all the LP spaces are in fact Banach spaces, and then we will see later when they are reflexive, when they are separable, and all these things in certain cases. So what is an important corollary? We have that, so let x s mu be a measure space, okay, and let fn converge to f in LP mu. 1 less than or equal to p less than or equal to infinity. Okay, then there exists a subsequence f and k such that 1 f and k converges to f pointwise. That means f and kx converges to f of x almost everywhere, that is except on the set of 0 for all x this happens. And 2, you have that mod f and kx is less than or equal to h of x almost everywhere for some h in LP of p. So proof: obvious if p equals infinity. In fact, entire sequence has this property, because we have shown that the entire sequence converges and therefore we didn't even take a subsequence. So if 1 less than or equal to p less than infinity, then we saw there exists an f and k which converges to f tilde pointwise, and f tilde is an LP, and f and k converges to f tilde in LP mu, of course. Okay, we saw this. But then you are given that fn converges to f, and therefore this implies f equals f tilde almost everywhere, that is f equals f tilde in LP. Therefore, the first one is proved, namely you have a subsequence which converges. So this is a very important property, very useful property in studying convergence in LP spaces. So if you have LP convergence, then for a subsequence you have pointwise convergence. Okay, so LP convergence is some convergence of some integral to 0. Okay, what does fn go into LP? So it means that mod fn minus f power p d mu over x goes to 0. So this is something about the integrals, whereas I am saying then that you can find a subsequence which converges pointwise except on a set of measure 0. Now for the second part, you just take h equals f tilde plus g, where g is the function, that infinite series which we defined in the proof of the theorem, g as in proof of the theorem. Then h is in LP, and in fact mod f and k is less than this. It's just triangle inequality, and that will tell you this. Okay, so we now have the Banach, LP is a Banach space, and then we will see various other properties of what are the duals of the LP spaces, when is it separable, when is it reflexive, and what are some other properties of this. Okay.